All right, so here's where limits get fun. Okay? Or maybe you're already having fun. I don't know. This is our informal definition of continuity. Okay? What does it mean to be continuous? If a curve is continuous, we have no breaks or holes in the graph. We can essentially draw our curve without lifting a pencil. Or our pencil, pen, whatever you're writing. Okay? Here we have a continuous curve. We can just trace along it without lifting our writing utensil. Here we have an issue with a break and a hole. Both of those things are making our curve discontinuous. Okay. What kind of functions, what family of functions will always be continuous? What family of functions will always be continuous? We can draw them without lifting our
Sine and cosine function.
sine and cosine are continuous. What else? Okay, brainstorm with your table for 10 seconds.
What about the no, that's right. No? Pretty much.
All right, back up together. Pot of one, what you talk about? Polynomials. Are polynomials in general always continuous? X squared, x cubed, x to the fourth, x to the fifth, all of those. They're always continuous. Okay? Any others mentioned? Part two? Okay. That's a safe answer. Part two, anything else? Tangent. Tangent has asymptotes, right? And so tangent, which we're going to talk about here in a little bit, I'm glad you brought that up. The tangent graph actually is not continuous because it has a bunch of asymptotes, okay? So we'll come back to that. In general, polynomials are always going to be continuous. Anytime you have a rational function, it's always going to be discontinuous. Because what can happen with a rational graph? One of two things. Either there are holes or asymptotes. Okay, and there could be one hole or one asymptote. But no matter what, if we have a fraction present, we know there's going to be a hole or an asymptote. That's going to make it as a function discontinuous. Okay. Now, on the next slide is the formal definition of continuity. This is another one of those definitions that is very important to know because we're going to have to use it to prove things, and you are going to have to explain it to me. Okay? It's one of those definitions that we're going to have to use in a few different ways. Okay, we're going to have to use it to prove that things are continuous. We're going to have to use it logically. Okay, so each piece is very important. Okay, it's also a question that I'm going to ask you. All right. So the definition of continuity. There are three pieces. Is there a glare from the sun? Okay. It hasn't been like super sunny the past couple of mornings. There we go. Okay, a function is continuous at C if these three are true. The function is defined. That means we have a coordinate there. The limit exists. Okay, so right and left hand limits are the same. And the limit is the function value. Okay, I'll let you write that down and then we'll talk about it again. you wouldn't have to write that last part. Okay, so when we talk about continuity, the function value has to be defined, which means we have to have a coordinate there at C. Okay, the limit exists, which means from the right and, excuse me, the left and the right hand side, we're approaching the same thing. And on top of that, those two have to be the same value. That function value and limit have to be the same thing. Okay? So what I'm going to do is I'm going to show you some counter examples of each of the three definitions so you can see what it looks like when we're not continuous. Okay? This down here is talking about continuity on an open interval. If I say it's continuous from A to B, then from A to B, we have continuity. If I say we're continuous everywhere, that's on the interval all over. Okay. All right, so this picture, we do not have continuity between A and B because at C, we don't have a function value. There's a hole there. And so it is discontinuous. If we draw this out, we have to lift our pencil to get over that hole. Okay, so this is not continuous because the function value isn't there. Here, now we do have a function value at C. However, the right and left hand limits are not the same, and so it's not continuous. This is probably one of the more obvious examples of discontinuity because we have that break in the graph. Okay, it's easy to see that that limit does not exist. And then here's the third counterexample. Here the limit exists and the function value exists, but their values are not the same. Okay, so we are discontinuous here. So I made you open your book to page 79. There are the first 6 homework problems. I had you look at the right and left hand limits Tuesday evening, I think. And then I said, well, I forgot to say, don't worry about continuity because you don't know what it is. But I want to give you about a minute for you and your group to look at 1 through 6. I want you to decide which ones are continuous and which ones are not continuous. All right. Pod 1 is number 1, continuous. Yes.
Yes.
Excellent. Pod 2, number 2. Yes. Pod 3, number 3. Why is it not? Okay, the function value is different than the limit. Good. Pod number 4, number 4.
No.
No, why? Okay, so f of c is not the same as the limit as x approaches c. Very good. Pod 5, number 5. You didn't have a book. Why did that get solved? Number 5. Look at it. We'll come back. Number 6.
No.
Why?
Break.
Okay, which one of those three things does it,
Doesn't exist.
the limit doesn't exist, is that what you said?
Yeah.
The limit doesn't exist. Okay, pod 5, back to you.
No.
Why? Limit doesn't exist at 2. Excellent. Okay? These three graphs, okay? Pod 6 already, Hugh, was it you that brought up sine and cosine?
Yeah.
Sine and cosine will always be continuous everywhere. Okay? We already kind of talked about this one. Hey, here's that graph again that we had to look at a couple days ago, the semicircle. Is it continuous where we have our domain? Okay? It's continuous on its domain. We could say that it's continuous from -2 to 2. Okay? Since those endpoints are included and like the left-hand limit exists and the right-hand limit exists here, obviously, since our function doesn't keep going, we can't talk about the limit at -2. But since our endpoints are the same as our one-sided limits, we can include them in continuity. Okay? This example right here, is it continuous? No, but we could say it's continuous from 0 to 1, right? And it's continuous from 1 to 2, and it's continuous from 1 to 3. But as a function itself, it's not continuous. That's pretty obvious. Okay? All right, so what can we do with that definition of continuity? Okay, this is a type of example that you're going to see often. On your AP test, there's probably going to be some sort of question, whether multiple choice or free response, that looks similar to this. Okay, we have a piecewise function, and we want it to be continuous. Okay, so let's use the definition of continuity. Okay, what's probably the most important thing to check first?
The limit exists.
Okay, so let's make sure the limit exists. So where are we worried about the limit existing, Q? At 2. So let's look at the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. From the left, we're talking about this piece right here, correct?
Yes.
Yes. So a times 2 squared would be 4a. The limit as x approaches 2 from the right, that's this piece right here. We're going to plug 2 into x plus a. Okay. Now we want, our goal is to figure out what a is. So if we want this to be continuous, what do we want to be true about the right and the left-hand limit? We want them to be the same. So we should probably set our left-hand limit equal to our right-hand limit. What is a? Anybody? Thank you. A is 2/3. Questions? Okay. Let's just make sure our function value exists. Since we have equality here, if we wanted to evaluate f of 2, we would plug 2 into this piece right here, a times x squared, right? 2 would be 2/3 times 4, which is 8/3, right? If we go back up here and look at what our limit actually is, our limit from the left is 8/3, our limit from the right is 8/3, our function value is 8/3, we have continuity, okay? But what we're really, I mean, this is what the goal was right here. Okay, we need to talk about the types of discontinuity. There are 2 types of discontinuity, okay? We have what's called removable and non-removable discontinuity. If it is a removable discontinuity, we can rewrite the function to make it continuous. If it's non-removable, then there's no way to fix it. It's always going to be continuous. I'm going to give you pictures of each of these. Okay, and these definitions are going to be on the slides that I'm going to show you. So here is a removable discontinuity. Basically, if you have a hole, we can rewrite it to fill it in, right? Like this looks like the line x plus 1, except it has a hole. So if we rewrote it as x plus 1, we'd have the same graph that would be continuous, all right? So if there's a hole, it is a removable discontinuity, okay? And when do we get holes?
Things cancel.
Okay, when our factors cancel from numerator to denominator, okay? So a non-removable discontinuity, any guesses?
You're right there.
Okay, but yes, I've already told you that. Picture, what would it look like in a picture?
That's right.
This is what you're thinking. Like an asymptote. Okay? Asymptotes are going to be non-removable discontinuity. Holes are going to be removable. So it's going to be important for you to be able to look at an equation or a graph, determine if it's continuous and what types of discontinuity we have. All right? First example. Okay, I told you we'd come back to the tangent of x. Okay? When we think of the tangent of x, usually we think of this, right? But what we have to remember is that this is what the graph looks like, correct? Over and over and over and over again. Okay? A couple ways we can think about the tangent of x. You can think about this graph right here. Okay? And we obviously know that there are asymptotes. We can also think of the tangent being the same thing as sine of x over cosine of x. And remember, anytime we have any sort of a rational function, like we have a fraction, where that denominator is 0, it's going to be some type of discontinuity. Okay? So we have removable discontinuity. Okay? Where do we have discontinuity? Where are they? Pi over 2, 3 pi over 2, 5 pi over 2, all of those, right? So we have removable discontinuity when x is pi over 2 in intervals of pi, right? That's where our denominator is 0. Okay, pi over 2, 3 pi over 2, those are pi apart.
Why is this one removable? Because it has the asymptote.
Oh, I even said non. It's non-removable. Thank you for pointing that out. It is non-removable. Too many letters are right up there. It is non-removable since they are asymptotes. Thank you, Logan. Okay. What about number 2? What kind of function is number 2? It's a cubic, which is in which family? Polynomial. What did we say about polynomials? They are always continuous. Okay? Okay? Next 2 examples. Okay. Number 3, we're talking about a fraction. We know it's going to be discontinuous somewhere. Okay? What should we maybe do with that fraction before we right now decide where it's discontinuous? We need to factor and see if anything simplifies. Okay? Can anything simplify? Okay? Which means what about our graph?
The whole of it.
We have a hole, which is what kind of discontinuity?
Removable.
Okay. So we have a removable discontinuity at x equals 0. What's happening at x equals 1? There's an asymptote, okay? Since we didn't cancel out x minus 1, it's still in the denominator. There's an asymptote there, which means we have non-removable discontinuity. I'm not going to spell that word out again. At x equals 1. We have a hole at 0, so it's removable discontinuity. We have an asymptote at x equals 1, so that's non-removable discontinuity. Okay. All right, what about number 4? What are we going to have to do to determine if this one's continuous or not? Can you be a little bit more specific than plug in 0? Okay, we need to see if that limit is existing, right? So, more practice for this. The limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. Okay, so from the left, we're going to plug 0 into the first piece. What's our limit? From the right, we're going to plug 0 into the second piece, which is 4. So So the limit as x approaches 0 is 4. We know the function value at 0 is also 4. I already did that when we did the limit. So what's true about this graph? It's continuous. If that limit didn't exist, it would be discontinuous. Okay. All right, one more example we are going to talk about. Composition. We have f of x is x plus 8 over x plus 7. G of x is 3x. If I asked you just about f of x, is f of x by itself continuous?
No.
No? Where is it discontinuous?
X equals -7.
X equals -7. At x equals -7, we have an asymptote, so we are discontinuous. What about g of x? Is g of x continuous? Yes, it's in that polynomial family. It's a line. It is continuous. Okay? Let's talk about the composition. F composed with g. We are going to plug 3x into our function. There's our composition. Is this continuous?
No.
What is this?
No.
Cole, where is it discontinuous?
It is discontinuous at x equals -3,7. Like it's no other way around. Yeah, it should be, yeah.
Is that better? Okay. And you said it's discontinuous. What kind of discontinuity is it? What's happening at -7/3?
Non-removable.
Oh, no.
Okay, it's non-removable because we have an asymptote. Okay, on the next slide there are some, excuse me, there are some rules that I don't want you to write down. If you need to reference them, they're in your book. It's kind of the same thing when we talked about the property of limits. Something we need to talk about, but not necessarily something you need to write down because I think some of them are a little intuitive. So if we have continuity of a function at C, then, and we have continuity of a function, two functions at C, when we add them together, we're still going to have continuity at C. If we multiply them, we're still going to have continuity at C. If we divide them, we're still going to have continuity at C. We're just going to have discontinuity at wherever we divide that. Okay. That's you're probably not going to see that like really being used a lot, but just so you know, when we combine functions that are continuous, they're going to stay continuous where you combine them. Okay. So this is what I have for you. Oh, yep, forgot about this. Okay, another AP question. Okay. On the AP test, you will get a handful of questions that give you a question, give you 3 options, and you have to decide which ones are either true or false. Okay? So as a pod, I would like you to discuss this question and decide on an answer. Okay? I'll give you about a minute and a half to discuss this question and come up with an answer. Okay? Okay, what I'd like you to do is, as a class, you need to show me your answer. So is it A? Is it B? Is it C? Is it D? Is it E?
Can you do that E one more time?
Show me your answer. This is B, this is D. Okay. Give me an answer. Come up with something. Is pod 6 and pod 5 the only people who got an answer? Okay, you're not impressing me right now. Yes, at least. It's okay to guess. Okay. So if you're saying C, you're saying that the only thing that is true is that there is a vertical asymptote at 3. Did you consider trying to simplify that function?
Yep.
What's happening at 3? There is a hole. There is not an asymptote.
We were right. That's what we said.
No. No. Cole? No. Okay. Now, so really what we have is this is the line x plus 3, but there's a hole. So now we need to decide, does the limit exist and is it continuous? All right? So does the limit exist? If we take the limit as x approaches 3 of this function, does it exist? Right? Essentially, what is happening, we have x plus 3 is the line, but there's a hole at x equals 3. Where is that hole? 3 what? 3, 6. If we plug 3 in, it's at 3, 6. Now, this is telling me that we also have the coordinate 3, 6. So what's happening is the limit exists because we're approaching that hole. This is a coordinate at 3, 6. Are we continuous? Two is correct because this is the coordinate filling in that hole. Okay? So I just wanted you to I'm going to start exposing you to these types of questions. These are the things that you're going to have to think about. Like, you may know, like, how to do a problem, but you're going to have to think about what everything in that problem means so you can answer these true or false type questions. Okay? Now, something that we have not talked about in 1.4 is called the intermediate value theorem. So on top of the homework that I'm assigning, I have a very quick little worksheet where you're going to basically come up with what the intermediate value theorem is. Okay? Instead of me just telling it to you, I want you to think about a couple of things. This worksheet will kind of guide you through the things that I want you to think about. And that homework should be on your goal sheet as well. So we have the intermediate value theorem. This should take you less than 5 minutes to go through. You have some book problems. I've highlighted and underlined the ones that are the most important. You should do all of them, but if you run out of time, do the bolded ones. And then your limits redemption worksheet will be due on Tuesday, but if you need to ask questions, tomorrow would be a good day to do that. Okay?